Alright, welcome to the Chapter 20 physics video for Grauer School of Physics. This one is going to be starting our new unit on static electricity, and I'm going to go through it relatively quickly with the assumption that you'll be able to pause and copy down the notes if needed. Otherwise you can go quickly just to get through the content if you're reviewing it. Alright, so we've already learned about some of this stuff, or talked about it in class, but we're going to start with charges and forces. What are the concepts there? So it turns out in nature, if you take two things and you rub them together, a lot of times after you've rubbed them, they'll attract to each other, or if you take two different things that have been rubbed, sometimes they'll repel. A good example of this that you might be aware of from everyday experience is in the in the dryer. After you take your clothes out of the dryer, a lot of times they cling together or some things will repel from each other. And so we try to understand, okay, well, what's causing this to happen? And so what we can kind of do is identify that something is on these objects which is making them attract or repel, which is therefore causing a force. And after lots of experimentation, which we will do in class to kind of conclude the same stuff, but the results end up being that there are only two different types of charge. Like charges are going to repel, and opposite charges are going to attract. And a neutral object just means it has equal amounts of positive and negative charge. We'll identify them as positive and negative in a second. So it has equal amounts of positive and negative, and so overall its charge balances out. But we'll see that even neutral objects can still interact differently than an object would be if it had no charge at all. Okay. We can also now classify materials into two categories. They are going to be electrical conductors and electrical insulators. So the difference is just like a thermal conductor or a thermal insulator, they allow or do not allow heat to flow through them. So, the thermal one would allow or not allow heat to flow through, and so an electrical conductor or insulator would allow or not allow electric charge to move through it. So an electrical conductor allows charge to move through it. So if you just have a single object and it's a conductor, the charges are trying to get away from each other because like charges repel. So all the ones are trying to escape, and they're going to push themselves out as far as possible. So that means they're going to go out to the surface of the object because that's as far away as they can get. On the other hand, an insulator, it does not allow the charges to move. It can still get charge added to it, but the charge stays in whatever place it was added. A good example of this is when you take a balloon and you rub it on your hair. You build up charges on that spot on the rubber of the balloon, but they don't spread out over the entire balloon. They just stay in that one localized spot. Whereas if you had, say, like a metal sphere and you rubbed it on your hair, if it did get charged, the charge would spread out over the entire thing because metal is a conductor, whereas rubber is an insulator. So the excess charge stays localized if it's an insulator. If it's a conductor, the charges can move. So in most cases, this is important to understand more from a small scale point of view, which we're going to get to the movement of charges in a couple of chapters, but since the way that atoms are structured is with the protons in the nucleus and the electrons kind of whirling around the outside, the charges that typically get moved or transferred when there's a transfer of charge are those electrons. So you probably learned in chemistry class you can have valence electrons that can be ionized and they can be taken off, or they can be shared among different molecules. So in this case it's the electrons that are moving around, not the protons. In not all cases, but in most cases with electric circuits and that kind of stuff, it's the electrons that are moving. Okay, there are three ways that you can charge an object. The first one is by friction or rubbing, which we just talked about. Clothes in your dryer, or if you have a PVC pipe and a rabbit fur, you rub them together, they'll get charged up. Anytime you rub these two kind of objects together, the electrons will be more strongly attracted to one of the objects than the other one, and so they'll get transferred from one to the other, leaving it with one object positive and one object negative. So the result here is you have one positive object. Sorry, it's been a while since I did these, so my handwriting is bad again. And you'll have one negative object. And since I'm lazy, I almost never write positive and negative, and instead I just write a plus sign or a minus sign, and I usually put brackets or parentheses around it. Okay? Charging by conduction just means direct contact between two objects. So if both of them were neutral and you touch them together, nothing would happen. But if you have one object that's charged positive and one object that's, say, neutral, and you touch them together, some of the positive charge from the positive object can get shared and transferred over to the other object, leaving them with both the same charge. So both end up, both end with the same charge. same type of charge, I guess. It doesn't have to be the same amount. The amount depends on the shape and material and all that kind of stuff, but they will definitely both end up with the same charge. If they're touching each other, you won't have one stay positive and one stay negative because the charges will attract and transfer to the other side. So charging by induction, it's typically called charging without contact. I put these asterisks here because actually when you charge something by induction, you don't touch it to the other object, but you do have to touch it to ground. So it's kind of complicated and requires a larger picture. So on the next slide, I'll explain charging by induction in a lot more detail. And coupled with charging by induction is this idea of an induced dipole. Okay, so an induced dipole means induced means to cause something to happen, and a dipole means that you have two separate poles, which means the charges have been separated. So positive is on one side and negative is on the other side. And this can be seen in conductors or insulators, and an electroscope is a good example of how or when this would occur. So an electroscope, you've got a solid ball on top, and you've got a jar here, and then inside you have two thin metal foils. Okay, so this is all neutral, but it's a solid ball connected by a conductor to these two thin metal wires. So if you bring up something with positive charge, what happens is in this metal here, the negatives are going to come up because they're attracted. They're going to come up here, leaving behind positives on these wires, and then these two wires, because positive charges repel, they will push away from each other. The same would happen if you brought in negative. You would attract the positive, leaving behind negative, which would again repel. So an electroscope, it can't really tell you whether the object is positive or negative, but it can tell you if it's charged or if it's neutral. If you were to bring a neutral object here, where's my mouse? If you were to bring a neutral object here, it wouldn't attract or repel. This would stay neutral, and the two little wires dropping down wouldn't move at all. But if you bring a positively or negatively charged object close to it, it'll cause a dipole. So this is a dipole where you have the negatives on one side and the positives on the other side. This separation of charge within a single object onto the two different sides of the object, that's what a dipole is. Okay, so now let's talk about how a dipole can lead to charging by induction. So if we have a charge here, say positive, and then we have some neutral object here. Oh, I spelled neutral wrong. Sorry. N-E-U. If we have a neutral object here, as soon as we bring this charge in nearby it, what's going to happen is within this object, it's still neutral because these haven't touched, but the negatives will be attracted to this side, and the positives will be pushed away to this side. And there's still a lot of positive and negatives mixed throughout the entire thing. Obviously, it's made of atoms. They have positive and negative charges. But the net overall result is that there will be more negatives on this side and more positives on this side. Imagine if I take these two things, positive and negative, and I shift all of these this way, and I shift all these this way. On this end, there's going to be a stripe of one type, and on this end, there's going to be a stripe of the other type. Okay, so right now, this object is neutral, but it has an induced dipole, so the charges are separated side to side. And we're not supposed to touch these because charging by induction says no contact. So we don't ever touch these to each other. But what we do is we connect this piece of metal to ground. And hopefully you've read about ground in your book already, but if not, ground is basically a reservoir of lots of positive and negative charge. So it has basically an unlimited amount of positive and negative. It can accept positive or negative, and it can give up positive or negative as much as needed. So it's basically just a giant reservoir. So what can happen now is these positives, they can leave because they have a place to go that can accept them, so to speak. I mean, this is very colloquial, but that's essentially the way that I can use to easily remember it. These positives, they all leave because they're getting pushed away, and likewise some negatives in the ground might get pulled up because they're being attracted. So whichever way you want to think about it, positives being pushed out of the object or negatives being sucked or pulled up into it through this conducting wire, that will end up giving you this positive guy is here. Now this guy is negative, okay, and it's still connected to ground. Now if we sever this connection, what we're left with is a negatively charged object. And then this positive charge, we can take it away, and this thing is still negative. So without ever touching this positive guy to this neutral object got charged opposite of it by connecting it to ground while in the presence of this charging object, whatever this other one brought. So if we would have brought in a negative guy, then the negatives would have been pushed away, positives would have been pulled on. So what always happens is you end up with the opposite charge of whatever object was nearby. So you end up with the opposite charge of whatever was nearby. So you should try to understand and kind of memorize, or if you understand it, you don't have to memorize, this process of charging by induction, and how it uses the concept of an induced dipole, which is the separation of charges to the two sides. Okay, some more important information to kind of build our understanding for this unit on charge and electricity. We have to have a standard size or unit. So the SI unit that we're going to use for charge, an amount of charge, is the coulomb. That's named after a scientist, Mr. Coulomb. And that is actually a pretty big amount of charge. And so in the real world, what are the increments of charge that we have? And it turns out that in the real world, the smallest unit of charge that's easily obtained is 1 electron. So that's called the, elementary charge. So the elementary charge is 1 electron, and every other large macroscopic object is an integer increment of this charge on the electron. So you could have something that has 72 electrons or 837,000 electrons, but you won't have anything in nature with only just a fraction of an electron. So this is really the fundamental smallest charge. But because electrons are so small, and in real world situations we have so many of them, you don't want to have to say that the charge on your object is 8,432,000 something electrons, right? So the unit that we use, the coulomb, is much, much bigger than 1 electron. So our conversion factor between electrons and coulombs is this number, 1.6 times 10 to the negative 19th. That's how much charge is 1 electron. To find out the number of electrons in a coulomb, you can do 1 over this, or flip it upside down. And that will convert from coulombs to electrons instead of electrons to coulombs. So that's important. You're going to be using coulombs all the time. Number of electrons every once in a while, but usually it's coulombs, because that's the SI unit. Okay. Another important thing is that charge is conserved. That means the total amount that we have is the beginning of any situation is going to equal the total amount we have at the end. It can get moved around. In fact, it will get moved around a lot, and tracking where it gets moved is a big part of electronics. But you can't create or destroy a net positive or a net negative charge. We'll learn much later on that you can create charge in the sense that you can create new particles, but you always create them in pairs of 1 positive and 1 negative that are equal and opposite, so that the net overall charge that you created was 0, or when 2 particles collide and annihilate each other, it always has equal and opposite charge, so the net charge doesn't change. Okay? How do charges behave when we combine them together? Well, we already said that like charges repel, so they want to get as far away from each other as possible. So if you have a weird shaped object, like say you have some weird shaped object like this, it may not be clear what distribution they'll have to get as far away as possible. And in fact, a problem like this requires quite a bit of calculus to figure out the exact distribution of how they will spread out to get as far away as possible, which is essentially trying to reduce themselves to the lowest energy state. But the one thing that we can talk about is a sphere, because it's a nice symmetrical shape. So if you have a perfect sphere, and pretend that's a perfect sphere, because it's symmetrical in all 3 directions, the charges will spread out uniformly to the surface and equally all around it. And interestingly enough, we can prove using calculus that that distribution of equally spread out over the surface of a spherical object has the exact same net effect as if all that charge was concentrated at a point in the center. Okay? So in physics, a lot of times, we'll have macroscopic large-scale objects, but as long as we make them spherical, we can pretend that they're a single point at the very center of the sphere. So when you're talking about 2 spheres and you say like they're both charged up such and such, the distance between them is the distance from the center of one to the center of the other one, because you're pretending this entire sphere is just a dot in the middle, and you're pretending that this entire sphere is just a dot at the middle. So any spherical distribution, you're essentially assuming it's a dot in the middle. Okay? If you have equal and opposite charges, or just a certain amount of positive and a certain amount of negative, they'll try to kind of combine and neutralize. It doesn't mean that the charges are gone, it just means if you put a positive and a negative right on top of each other, their electrical effects are essentially neutralized, because if there was something nearby, it would try to be attracted by one and repelled by the other, and the net effect, if they're positive and negative are right on top of each other, is that those two forces will balance out. So it will be as if they weren't there. So the charges are still present, but inactive in the sense that they're not causing any forces on their external surroundings, unless you create an induced dipole and separate them, and now you can have a force. Okay, so let's do a small example. What happens when you combine different charges? Suppose we added 10 nanocoulombs, remember n is nano, to the upper left box. So here we have 10 nanocoulombs, 8 nanocoulombs to the upper right box, and -6 nanocoulombs to this box. What would the charge on each box end up being? So how will these charges move when they're exposed to a situation like this? If we assume that these boxes are equal distance apart and all the same material, we still kind of have to ask ourselves, can the charges get from here to here? It depends what this material is made of. So if these 3 rods are insulators, then the charges can't move and they'll stay exactly how they are. So that's kind of an easy answer. So what if the charges are allowed to move because these 3 rods are conductors? Okay, if that's the case, you have to look at the total charge. You have a positive 18 and you have a -6. So the net result is that you have positive 12, because these -6 will cancel out or neutralize some of these positive charges. So the net effect is we have positive 12 nanocoulombs, and if these are all equal size and equal distance, it will spread out evenly, so you'll end up with 4 nanocoulombs per box. Again, there's a lot of other factors that might go into making that different, like the size and shape of the boxes and how far away they are from each other. But if everything is uniform and symmetrical, then the charges will spread out evenly, 4 on each box. Okay, let's do a sample problem here. A plastic rod is charged up to -20 nanocoulombs. Have electrons been added to the rod or protons removed? Well, if it's a negative charge, either electrons were added or protons were removed, but since we know that the thing that's carrying the charge and moving around is typically electrons, then we would say electrons have been added. How many electrons or protons have been added? Okay, we have to convert -20 nanocoulombs into a number of electrons. So we have our conversion factor. 1 electron is 1.6 times 10 to the -19th coulombs. Okay, coulombs cancel. You have to make sure that you write nano as times 10 to the -9th. And then type this in your calculator. I'm not actually sure what it equals, and I don't have a calculator here handy. But 20 divided by 1.6 is probably like 13 or something. And 10 to the -9th, 10 to the -19th, 10 to the 10th electrons. So 13 times 10 to the 10th, that's 130 times 10 to the 9th, 130 billion, roughly. This is an crude estimate. Electrons. And if you don't want to write out electron, you can do E with a little minus sign, almost as an exponent, E negative. That means electron. And then E positive means proton, although it's not as commonly used because it could also be positron. But E minus is definitely electron. So we've added about 130 billion electrons to this rod if it has a charge of -20 nanocoulombs. And I can tell you that's pretty small. -20 nanocoulombs is quite a small amount of charge. Yet it's still 130 billion electrons. So the amount of actual movement that we're talking about is massive. Okay. Now let's talk about the forces exerted in a mathematical sense when you have these charges distributed in a certain way. So Coulomb's law is the name of this equation, and it tells you the force. So we call this, I typically write F electric, and you've got your K. K is a constant, and it's 8.99 times 10 to the 9th Newton meters squared per coulomb squared. Typically we just round this whole thing to 9. That's close enough for all of our type of calculations. And then you've got the two charges, Q1 and Q2. So you can only have a force to exist between two objects, so you need both Q1 and Q2. And notice these absolute value bars. This equation is only going to tell us the magnitude of the charge, not the direction. So you have to use common sense and remember that opposites attract and like charges repel to figure out which direction it's going to go. I mean, it depends. If the two charges are above and below each other, the forces will be up and down. If the charges are side to side, the forces might be left to right. So the direction depends a lot on how you've drawn the picture. And you should draw pictures for these type of problems. So you got k, q1, q2, and it's divided by r squared. So it's very similar to the equation for gravity. Remember, gravity, universal gravity, was g m1 m2 over r squared. So the charge q1 and q2 takes the same role as the mass m1 and m2. You've got a constant of proportionality k, got a constant of proportionality g, and then you've got the distance squared. So both of them are an inverse square law. Okay, I said to help with calculations we can use the superposition principle. If you've forgotten what that is, all the superposition principle means is that if you have multiple forces acting all at the same time, you can calculate each one completely individually and then do the vector sum at the end. So you might have 3 or 4 charges all spread out. You can find the force between charge 1 and 2, 1 and 3, 1 and 4, 1 and 5, and get all those different forces and then add them up as vectors to figure out the overall net result. Okay, sample problem. A small glass bead has been charged up to 20 nanocoulombs. A tiny ball bearing 1 centimeter above the bead feels a force downward. What is the charge on the ball bearing? Okay, so a small glass bead is charged up to 20 nanocoulombs. Let's draw that guy. A tiny ball bearing 1 centimeter above it, so this is going to be 1 centimeter, center to center, feels a downward force, electric force. So this is F electric is 0.018 newtons. What is the charge on the ball? So what is this charge? Q. Okay, the fact that this force is downward and that the bead is above it guarantees that these two are attracting, which means this is oppositely charged. So the sign we know is going to be negative. Now let's find the magnitude. We have the formula, Coulomb's law, F equals K Q1 Q2 over R squared. If we want to solve for Q2, or call this Q1, doesn't matter, multiply R squared up here. So we have F R squared, divide by K Q1, and that equals Q2. Now we can plug in all of our numbers. 0.018. Radius is 0.01 because it's 1 centimeter, so convert that to meters squared. K is 9 times 10 to the 9th, and Q1 we said was 20 nanocoulombs. That's 20 times 10 to the negative 9th. So the one cool thing about this constant for Coulomb's law, times 10 to the 9th, is that if you have something with a nano in it, the 10 to the positive 9th and 10 to the negative 9th will cancel each other out. So that's kind of nice. Okay, so we type all this into our calculators. We're dividing by, I don't know, 0.018 times 0.01 squared divided by 20 divided by 9. That's going to give you your final answer. Again, I don't have a calculator, I apologize. But if you type this in, then you definitely got it right. And the units we're going to have are coulombs. And remember that this is a negative. So negative of whatever number you have. Fill in your answer, and then coulombs is your answer. Okay, another sample problem. 2 protons are 2 femtometers apart. What is electrical force on each one? So we've got proton 1, that's E positive, and we've got E positive, and they are 2 femtometers. Femtometers very, very close together. So this would be like inside the nucleus of an atom, for example. What is electrical force on each one? Well, F equals K Q1 Q2 over R squared. So we plug all this stuff in. 9 times 10 to the 9th. Q1 and Q2 are both 1.6 times 10 to the negative 19th. So since they're the same, I can just square that. And the distance away, 1 times 10 to the negative 15th. Square that, and we can get the electrical force between these two guys, whatever it is. And then it says what's the gravitational force on each one. So we'll have to find the force of gravity. Again, it's not mg because we're not on Earth's surface, we're here. So we need to use the universal law of gravity when these two things are very close together. So that's g m1 m2 over r squared. So g, if you remember, is 6.67 times 10 to the negative 11th, wasn't it? 6.67 times 10 to the negative 11th. I believe that's what it is. Mass 1, mass 2. So now it's important to remember the mass of a proton. So let me give you some information up here. Mass of the electron is 9.11 times 10 to the negative 31 kilograms. This is all in the cover of your book as well, but you might want to know. Mass of a proton, which is the same as the mass of a neutron, within a very large amount of significant figures, they're the same, is 1.67 times 10 to the negative 27th kilograms. So protons and neutrons are roughly about 2,000 times more massive than the electron, so the mass is a lot bigger. So put this number here, 1.67 times 10 to the negative 27, okay, squared, divided by distance is again 1 times 10 to the negative 15th, and that's squared, and you get an answer here. So this is force of gravity, and this is force electric. Okay, and you get these two forces. So I'm not going to do it here. Again, I don't have a calculator, but please, pause this video, take 1 minute, take your calculator out, and find these two forces. 1, 2. It's not that hard, and it's an important, valuable thing because you're going to see something crazy. So once you've got these two values, what is the ratio of them? Take this one and divide it by this one, and you'll see that the ratio, when you do this division, is extremely, extremely large. I think it's something like 10 to the 39th power, or 10 to the 40th power. So what that tells you is the electric force is way, 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 way stronger. No, maybe it's 10 to the 20th? No, it seems 10... Sorry, I don't remember. But the point is, the electric force is astronomically bigger than the gravitational force, which is a lot of times why it's called that the force of gravity is very weak. And you might think, well, how is gravity weak? You know, if I jump, I only go up 1 or 2 feet before I come crashing back down. But if you had an equal amount of charge, the size of the Earth and the size of my body, you know, they would be glued together so much that you could never even lift it a millimeter with that kind of force. So it's important to remember, and we'll talk about it a little bit, but when you try to press, like if I try to push my hand through, the reason that I can't go through is the electron repulsion between the electrons in my finger and the electrons in my hand. So anything that you touch or that feels completely solid like a rock, that is an electrical force repelling you. So if you think about it like that, it really is a pretty strong force that you can't get through. Alright. Okay, recap of key concepts, and we're done with chapter 20. You need to be able to convert between coulombs and electrons. Again, your conversion factor is 1.6 times 10 to the negative 19th coulombs. That's the charge on one electron. Okay, you should definitely know that electrons, in the vast majority of cases, are the charges that are moving around, and the protons are stationary in the nucleus. You should know that charges are conserved. The overall charge at the beginning should equal the overall charge at the end, but they will frequently get moved around from place to place. Along with conservation of charge is the idea that positive and negative cancels each other out. So if you start with 20 positives and 10 negatives, what you really have is a charge of plus 10, not a charge of 30. Like the charge, you have to say what sign it is. You can't just say an amount without saying what sign it is. Okay, Coulomb's law, that's the equation. F equals, say electric equals K Q1 Q2 over R squared. You should not only know how to use it, but you should also kind of remind yourself how to draw force diagrams and be able to do forces in 2 dimensions. So if you have, say, 3 charges that are not all aligned with each other, there might be forces downward and also forces sideways. So especially if you're taking the math version of this class, you definitely need to be able to do forces in 2 directions again, so refresh your memory on that. You should know that when the charge spreads out over a sphere, it acts as a point at the center of that sphere, and that we can calculate things by treating each force individually and then adding them up at the end. And it's very important when we say add them up, we're talking about as vectors. That means direction matters. So if you have a force positive 6 to the right and negative 3 to the left, when you add them, you're not doing 6 plus 3, you're doing positive 6 and negative 3. Or even more complicated is if you have forces in 2 dimensions, right? You have to use Pythagorean theorem and draw a triangle to add the forces as vectors. You can't just take the 2 numbers and add them together. Okay, so chapter 20 homework is going to be on the class handout and or emailed to you. And that's all we've got. See you soon for chapter 21.